Good afternoon, sir. Myself Prashant Galav, and I would like to introduce a new paper. This is a tutorial on powder XRD diffraction for the nanoscale material. The first point is the important implication of this PXRD is the phase identification. And it is done by comparing an experimental XRD pattern with a reference pattern that is either simulated or obtained from a database. In such case, an ambiguous and complete match between the experimental and reference is needed. And within this process, arbitrary peaks predicted by reference pattern cannot be missing in the experimental XRD without any justification. And to complete this comparison, experimental XRD pattern having sufficient signal to noise ratio are needed so that low intensity peaks can be observed. Due to its essentially identical diffraction pattern, phase identification can be difficult for some systems, especially nanoscale material. For example, gold and silver both are face-centered cubic metals, and the ores of the iron like magnetite and megamite, and this third is hexagonal close pack nickel carbide and nickel nitride. In the next part, we will discuss the lattice constant for highly crystalline bulk material with high signal to noise ratio and sharp peaks. The lattice constant are typically used up to 3 or 4 decimal place without the uncertainty error. To obtain such precise figures, profile fitting and refinement are necessary tools. For nanocrystalline material, having wider peaks and weaker signal to noise ratio and such accuracy in lattice constant is difficult. For example, by including a small amount of bulk crystalline compound such as LAB6, lanthanum, and boron compound in sample of alloy nanoparticle, the XRD pattern of the alloy nanoparticle can be compared more accurately by applying a 0-point shift. 0-point shift is nothing but is a technique in which we do uh, minor shifting of the x-axis for legitimate reasons caused by errors such as sample height alignment that is achieved by adding or subtracting a very small constant value. In this way, any changes in the peak position arising from the sample can be considered reliable because they change the relative to those of the internal standard which remains fixed. X-ray diffraction database versus simulated reference pattern. Since there are frequently many entries for the same phase, the particular reference file identification number should be provided when reference patterns from such database are used to compare with experimental data. It is possible to model PXRD pattern directly from crystallographic data, and software tools have the ability to include preferred orientation and peak broadening owing to the nanoscale crystalline domains. And the most important thing is that the downloadable zip file. Zip file means crystallographic information files can also be utilized to mimic XRD pattern and eliminate the need for human data entry. Amorphous versus nanocrystalline products. Amorphous components that lack long-range crystallographic order have an essential constraint that prevents them from being fully characterized by X-ray diffraction, which is a strong method for detecting crystalline phase in a sample. An XRD pattern for the sample that include one or more nanocrystalline components and a sizable amount of amorphous impurities might resemble a same pattern for the sample. Both would show comparable noticeable peak widening that solely contains the nanocrystalline components. In order to verify sample purity and identify whether any of the sample is amorphous, further characterization is thus required. And the third point is this sample purity. There are several methods for sample purity, but the limit of detection and quantification of standard laboratory X-ray diffractometer can range from 5 to 10%. These are only approximations and they may differ considerably depending on the instrument and the sample being described. This is the next slide is Shearer equation in which we relate the crystalline domain size versus the width of the peak. As the average, if the average particle diameter obtained by the TAM and the same sample is characterized by the XRD sample and the result of both these techniques are same, then we can conclude that we can conclude that the particles are single crystal rather than polycrystalline. Peak bonding only occurs between the bulk and between bulk 1 meter and 50 nanometer due to instrumental effects rather than particle size effect. But when we distinguish that these two effects, we have to use profile fitting. So profile fitting is the most important method to separate these two independent contributions. XRD pattern for spherical particles of nanoscale dimension will have the same relative intensities as the bulk material, but the peaks will be broad. Nanomaterial samples that include multiple distinct subpopulations of different sizes or shapes can produce more complex XRD patterns. As we can see in the graph, in which these three patterns of uh, of a same material, but these three patterns are corresponding to different planes. It is 100, this is 101, this is 002. 13 nanometer, 8 nanometer is the dimension of the material. For example, consider nanoplates of woodside that have average dimension of 13 nanometer and 5 nanometer and have the 001 plane as the base of the nanoplate. Here the crystalline domain size corresponding to 00L peaks is 5 nanometer. So the this plane is corresponding to 5 nanometer, and likewise H00 plane corresponding to 13 nanometer diameter of that material. And the second point is the difference in peak loading for different families of plane are consistent with the dimension and crystal orientation, uh, as we see in this in the first point, which reconcile the microscopic and bulk data to confirm that the nanoplate morphology comprises the majority of the sample. This figure shows the comparison uh, in which we take this sample in different orientation, different orientation. So this graph shows that orientation uh, affects a role in the in getting the pattern of the material. The figure shows experimental data for gallium sulfide nanosheets drop cast onto the XRD sample holder, which results in significant pivot orientation because the nanosheets tend to lie parallel to the surface of the sample holder. X-ray diffraction pattern of the sample prepared in different ways should have different relative intensities, corresponding to enhancement of related families of planes. Shows that the dropcast sample shows almost full preferred orientation, whereas the powder sample shows only partial preferred orientation. And the last image, this image shows that it is important to note that these two XRD patterns, a mixture of zinc blend and woodjade CDS and the woodjade CDS. This is the mixture of the sample, mixtures of these two, zinc sulfide and cadmium sulfide. The first three peaks are almost identical, like this. These three peaks are almost identical, the green one and the blue one. And the subtle features differentiate the two, including the presence of or absence of a few low intensity peaks. The zinc blend peaks overlap with some of the woodjade peaks, so the XRD pattern of the mixture appears to have higher relative intensity relative to woodjade for the peaks to which the zinc blend phase contributes. Thank you.